First of all, I heard my name much too much. But thank you very much for that. Now, wait a minute, where is the machine? Oh, here it is. All right. Very nice meeting. Very friendly, very warm. And I would like to thank all those who have contributed to this award for me. I want to cite somebody else. He's sitting there, Peter Gölitz, because he was very operational in starting these journals which go across countries. You know, for me, that's the Italian flag. That's my flag. I have always been very much European because these different cultures, these different countries, these different languages. But it's a battle of every day in Europe. I didn't want to say that, what I'm starting now with, but I would like to insist on it. And in fact, it happens that about 1 week ago, there was a new initiative which started in Strasbourg, which is called Europa Nova, trying to get a new impulse into things. Whether it will work out or not, I don't know. They asked me to participate. I usually have too many things to do already, but this is the thing I participate in. So just for you, a conclave in this famous eternal city, hang on to Europe. We are not alone in the world. We don't want to compete. We don't want to be bad girls, bad boys. But we have to stick together if we want really to continue to make this impact on the world. So, I have a number of people to thank, but I have already done some. And the other things which come later in the course of my presentation. First of all, you see here Primo Levi. For me, it is you could say another prize. No, it's not the case. Because Primo Levi was a chemist, okay. I have nothing against chemistry, quite to the contrary. Number two, he was also a writer, an artist, and art is one of the things which mankind has to really support. Be it music, be it painting. I just saw the Caravaggio. There's a famous Caravaggio in the Saint Louis Church, the French, what is called also the French church. A very nice Caravaggio, I must say. Others are nice too, but that one is especially nice. And finally, Primo Levi was what his people call a Mensch. Not just a chemist, not just an artist, a writer, but a human being. That's enough. That's what we should be. And as I said, with Peter Gölitz in the Bierkeller in Munich, with the help of the German Chemical Society, we started this strange thing, which was to try to bring people together in publication and so on. Okay, this morning I was giving a lecture at La Sapienza. It was a complicated lecture because I didn't know there would be a lot of students, but there were many students, and so I have been very careful now not to give overtime because I was very much overtime this morning. Now, wait a minute. That's it. Now, there is somebody else I would like to mention. Rita Levi-Montalcini. She had nothing to do with Primo Levi, as far as you know, unless, of course, when the name is the same, there must be some kind of relationship. She was like Professor Caetano. She was also, she got a Nobel Prize in Physiology and Medicine for neurobiology. So there's some strength. The ladies are very strong here. Huh? That's good. And she was also senator for life. But the title of my lecture is Towards Complex Matter, would have guessed that, and then had something to do with the periodic system. I will try not to get carried away, because otherwise you finish very late, but I will see. Okay, here is where we start. And we have to think deeply about that. There was the Big Bang, and now it has been almost experimentally established that it was followed by a cosmic inflation. In 10 to the minus 36 seconds something, the universe increased in size by 10 to the 78. You cannot imagine that. But that is what the measurements of the last thing, the Wilkinson, the Wilkinson probe of asymmetry of the background radiation in the universe has brought experimental support to that. So after that, then, once this started, physics came up. And this was the time of physics. No chemistry, no biology, no nothing like that. Chemistry started a bit later when it was cool enough to make atoms, molecules. Molecules got bigger and bigger and bigger. And then when it was at some stage, they separated, they made sort of primitive compartments. And chemistry had started and then led to more complicated assemblies. And life on Earth started around that time. As we know, that's the age of biology. So from physics to chemistry to biology, matter had become more complex. But now, there is even a much more complex period when thinking appeared. Without thinking, we would not be here. We would be running around in the fields and so on. It's nice, why not? It's nice to be in a meadow, eating grass, producing milk. But okay, we have something else. And without that, we wouldn't be here. And it's also something which, for me, is very difficult to understand, but it's a fact. How can this entity out there think back on where it comes from? Thinking back of your origin, that is something very difficult to understand that it can happen. And this is thanks to science. And one of famous person among these representatives of what we call human race, the human society, is Primo Levi. And he very well represents the ideal of what should be a human being. So the big question then we have to raise as scientists, I think you would agree that it is one big question. How does matter become complex? Up to us, and maybe further on other planets, in other galaxies, and so on. How can you go from an elementary particle to a thinking organism? And are there higher forms, perhaps, even of complex matter? We can represent that by this bridge. Some people in the audience, they know that I bring this up, this slide, they have seen it. This bridge represents, on one hand, physics, which deals with the laws of the universe. These are the laws on which everything else depends. Biology are the rules of life, not the laws. Physics answers the question, or tries to answer the question, why? Biology, how? And chemistry has a fantastically important mission. How can you go from the why to the how? It's a bridge expressing general physical laws in a living organism on a small planet in an immense universe. That is what chemistry has to do. Of course, we are all scientists first, but if we want to define what we can contribute, I think this is really the, let's say, the conceptual, the important contribution. Of course, we can make materials, we can make polymers, we can make drugs and so on, but this is really how can we go from these general laws to the expression of these laws. It is the answer to the question, and this is something which one can discuss. It gets philosophical, self-organization. In other words, our universe has, the laws of our universe are such that it will self-organize. It's not an accident. It is a cosmic imperative. I mention also Christian de Duve, who got the Nobel Prize for Biology. He had published a book that life is a cosmic imperative. I want to make it even broader. The appearance of complexity is a cosmic imperative in our universe. Now, people were thinking about these problems a long time ago. And let me just cite two Greek philosophers, 2,500 years ago. There was Empedocles. He said that the universe was built on 4 elements: fire, air, water, and earth. And the combination made properties dry, hot, humid, and cold. Okay, so it was a start. But at the same time, there was another person of the same time, more or less, who had a much deeper insight. It was Democritus. He said that matter is particulate, and there are particles that you cannot make them smaller. In Greek, that's atomos. You cannot make it smaller. You cannot break them. Okay, we now know that there are electrons, protons, and all that kind of things. But that was a big insight. In fact, sorry, let's get a bit longer. Democritus was said, and his followers, there are no writings of Democritus, that he had the idea in the following way. When you put water and alcohol on top of each other, in the morning, it's only one phase. So he said, come on, this cannot be continuous. It must be particles, they can mix. And this is said to be the way in which he was thinking, and I think that was quite deep, very deep. Now, many, many years later, particles and elements, what they were called elements, had accumulated, and there was a sort of a chaotic, a zoo, until some people tried to put some order. There was also a German, Lothar Meyer, but the one who had the best insight and the courage to go further was Dmitry Mendeleev, who in 1869 published a paper. At that time, there was a lot of German in chemistry, in the German Chemical Society, die Zeitschrift für Chemie, über die Beziehungen der Eigenschaften zu den Atomgewichten der Elemente and the relationship between the properties of the atomic weight of the elements. Here is the first way this periodic table looked, and they are organized in columns rather than in periods, like the representation we have now. And he had the courage to say, what we didn't find yet, we will find it. There are question marks, and they were found. Nowadays, this is what it looks like. This is a table. That's the most important table in our universe. Why? Because from 1 to 92 hydrogen to uranium, you see the elements, the other ones are artificial ones. You see what our universe is made of. And this is something very disappointing for me, because beyond 92, okay, even if you may admit that there's neptunium, plutonium, and so on, sure, why not? But there are still elements. And there's nothing between hydrogen and helium. There's nothing between titanium and vanadium. Just because it's arithmetics. one proton, one electron, two protons, two electrons. Of course, sometimes there's some neutrons coming in, but it's just counting. And it's very disappointing because it means we are limited. For a scientist, you have these things and you cannot have others. Your Lego set is finished. Of course, we can use it all making infinite number of objects because you can connect many of them, fewer and different ones and so on. But it is something which, it bothers me, I must say, to say that on our planet, in our universe, that's the way it is. And there's nothing between these bricks. You can say, okay, why not? Because I think we know now the structure of matter. We know how it builds up. What is even very astonishing is that we have discovered that. That is why I say just fantastic pictures in Rome everywhere. But that is the picture which is the most important for us. Nothing against the others, because they're beautiful, they're art, but that is the more profound one. Unfortunately, there's no other. That's the periodic table of the elements, as you know, and that's the playground of chemistry. We are children, we have a Lego set of 92 pieces, and now we play with it. Primo Levi chose some of them in his famous book on the periodic system. In fact, it's not the table. His book, the first edition, printing, was a system. And here are the ones which are in his book. So for those who want to write on the periodic system, there's still stuff to do. There's some work to do. You have many chapters left over. And okay, there's some Italian below, which I picked up from the internet, of course. Now, milestones in molecular chemistry. We have to build up molecules. Molecular chemistry is the art and science of making molecules from atoms. We can now just cite two milestones. One is Friedrich Wöhler. He was the first one to, it's admitted like that, okay. Man can sort of say maybe to other people, but Wöhler made urea from ammonium cyanate, and that was a chemical transformation, and he was very conscious of what he had done, even if it was very simple, because he wrote to, I don't remember to whom just right now, and he said, I was able to make urea without the help of any organism, being dog or human. Interesting way also to write. Then centuries later, 2 centuries later, maybe, we had this synthesis of vitamin B12, a very complicated molecule where the common efforts were necessary for two groups, Robert Burns Woodward at Harvard and Albert Eschenmoser in Switzerland at the ETH. I worked with Woodward at that time for 63, 64. And this was considered as a huge achievement in molecular chemistry. Of course, now people have made more complicated molecules than that, but it's sort of the emblematic, the way in which molecular chemistry evolved to high complexity. Now, are molecules the end of the game? No. When you look at biology, here I represent a cancer cell and 2 killer cells. The killer cells will detect the cancer cell and destroy it. They shouldn't make a mistake. So there is something which tells them, the killer cells, that the other one is a cancer cell. The same is when you have viruses, like the HIV virus. When it hits a white blood cell, it can penetrate. And we have another example, COVID-19. Huh? How do they know that the killer cells have found a cancer cell that the virus has now reached the target? There must be something between them which tells them a contact between the objects which make up these bodies, a contact between the molecules, and this is, of course, then the level which is supramolecular. Not that supramolecular chemistry is not a discovery, it's just a recognition that it exists. because it has always existed, of course. From the moment there was more than one molecule, supermolecular chemistry was there. In fact, I had just an interview, and usually when journalists ask me, can you explain to us what supramolecular chemistry is? So I start by saying, like there are molecules, there are entities, they react together. But the easy way to explain that, I'm sorry if I repeat it, but it's a water molecule isolated in the gas phase has no boiling point, no melting point, no viscosity, no any other property, dipole moment, and so on. A glass of water can freeze, can boil, has all these other properties. What is it? It's still water, but they are together, they interact, they bring up new properties. It's very simple. It's just, when you see a bunch of trees, usually you begin by collecting the trees. And at some stage you say, oh, there is a forest there. That's all, recognizing that there is a forest. So for molecular chemistry, we come to supramolecular chemistry. The first time I used that word was in 1978, but it could have been any time. And this is then mastering the interactions between molecules, and then it has to do with how molecules recognize one another, how a killer cell recognizes a cancer cell, and then also reactivity, how they react and how they carry each other. They can carry through membranes. Molecular recognition is the basis, and it is based on interactions. Think molecules have an interaction, and also on information. That is something which for modern students who think about information all the time, who have all these nice little objects in their pocket, which are information carrying objects and information storage, you have interactions, information, which means that you have a sort of a fitting together, which Emil Fischer, again, a German chemist, but he got his PhD in Strasbourg. At that time, we were German, That was one of the good things of these wars. We changed from one border to the other one. And the joke is that the Alsatians were always on the winning side. Because when the Germans won, we were German. When the French won, we were French. Okay, but it's not uncomfortable. It's a bit shaky, but all right. So he said in 1894 that for an action of an enzyme acting on substrate, they have to fit together like Schloss und Schlüssel, like a lock and the key. This is also something very easy to explain to journalists when they want to interview you. Now, this recognition is important, and of course, the most famous and for us the most important process is the storage of information in our DNA, in this strand of groups linked together in a long, long, long string. And here again, I said earlier that 92, that's not sufficient. We should look down. Here there are 4 letters. And with 4 letters, you write the genome of all living organisms. And these letters are trivial. They're not B12. They're much simpler. Adenine, guanine, thymine, cytosine. And they wrap around like in a double helix because they interact. So 4 letters are enough to write the genome of all human beings. On other planets, there can be other letters. And some chemists have started and trying to introduce other letters. But nevertheless, even if they succeed, we know that it's enough to make all of us and to read the information also by interaction. So chemistry is not just a science of a structure and transformation, how you make it and how you transform it, of living and non-living matter. Of course, before there was life, there was an evolution which was there because you cannot just jump from an atom to a living organism. And it's also an information science. The science, you can call that, you can have other formulations if you want, but the science of informed matter. Matter has information, And this information is what makes us. And it's written very simply. It's usually, come on, 4 letters. It's a joke that you can make all the human beings with 4 letters. But that's what it is. And the animals and the plants and so on. So the storage is at the level of the molecule, and the processing is at the level of interaction between these letters. They pair up. It's very simple also, just pairing. Now, of course, the question often asked, what is all that for? What is it good for? Of course, basic research, we want to have more knowledge. Applied research, we want to apply it. And in life sciences, there's something which I learned only recently. The first compound we made in the work on supramolecular chemistry was a cage, to put something in the cage. And it happens, this was a paper in the 1960s, that when you take potassium fluoride, that's for the chemists now, I'm sorry, but I guess all of you are chemists more or less. And when potassium fluoride is alone, the fluoride and potassium, they interact very strongly. If you put now the potassium in a big cage, the fluoride has to go out. So it becomes very unhappy, very reactive. And so we had studied this with Bernard Dietrich at that time and Jean-Pierre Sauvage. I learned that in Jülich and in other places where they make the labeled molecules for positron emission tomography, they use the cryptates. I would never have guessed it when we started it. You take potassium fluoride, you put the potassium in a cage, and then you can use it as a reagent. So that's a practical application. Another application is that a drug is a key for a biological lock. So you want to adapt the key, and a drug is that. With a drug, you want to influence, either inhibit or activate a biological molecule, a protein, an enzyme, or something. Then it happens also that somebody else, we had made some, with Vincenzo Balzani, he's a good friend, and we had studied the luminescence of europium sitting in a cavity. When it's outside in water, it gets deactivated by the water vibrations, so you don't see any fluorescence. But if you put it in a hole, in a cavity which protects it, you can make this as a label for medical diagnostics. And Gérard Matisse, who was a CNRS person from Nancy, he had also relationship with us. He made in a company, in a small company, SysBio, this apparatus which for medical diagnostics, which is now used in many hospitals. Gene transfer was another thing which we did, where we contributed something to helping a piece of gene to go through the membranes. That, of course, leads to genetically modified organisms, which is something which some people don't like, but I think we need it. We will use it. I'm sure we will use it. First of all, the easiest is for genetic diseases, because in genetic diseases, you can correct for the one which doesn't work. If you want to make new ones, then let's say it, you make diversity. Huh? You create diversity which doesn't exist yet. Which one you want to make, that's another question. But you can make genetically modified organisms which have other properties. Finally, biomaterials of supramolecular nature. This is also something when we developed supramolecular polymers, we did not know where it would lead. We just developed it. And then Bert Meyer in the Netherlands contributed to, we used 3 hydrogen bonds, he used 4 hydrogen bonds. At any rate, in 2013, supramolecular polymers were used for the surgical treatment of children who had a very severe congenital malformation of the heart. And here you see the first case. Dominika was operated on by Leo Bourquiria. Leo Bourquiria was, he still is, I suppose, at the Bakulev Center for Cardiac Pediatric Surgery in Moscow. Now, we don't go to Moscow anymore. It's a pity, it's terrible. Let's think about. I don't know what happened to him. I have good friends over there, and so what can you do? So beyond then supramolecular chemistry, you want to define rules which lead to self-organization, to make spontaneous but controlled by the molecular information objects which have new properties and which organize. And just to give an example of something which is really chemistry, not biology. Viruses are a bunch of molecules. They are not living. They are just a set of molecules like here, 2,130 bricks, protein units, and also a genome of the virus. If you mix them, they get together and you generate automatically the particle. It's really self-organization in the sense that it works by itself. By itself, you get this spontaneously. And of course, then one can think of many artificial things which can be done and has been done around the different laboratories. You can sort of say, program, if I want to use again the language of information, you can program your system. And it's really programming. We know that when we have a carbon, when we have an oxygen, we have a nitrogen, the program is quite fixed. So just to give you some examples, it was possible to make artificial double helix or triple helix, which has nothing to do with DNA. We just fun playing, be able to do it. Just, chemists sometimes, they like to show that we can do it. Objects like that, where you have metal ions like silver, organized in a grid-like fashion by perpendicular molecules oriented in that way, circular architectures, and also nanocylinders, things like that. And also the possibility exists that we may go from directly from the device, from the component to the device, which means that fabrication is replaced by self-fabrication, which is, of course, the ultimate way. After all, the virus does it. The virus is self-fabricating. It makes itself because the pieces are the correct ones. So, just to give one example of what we are doing now, I have talked up to now by doing chemistry by design, by inserting information and programming the system, which leads to what supramolecular chemistry has been doing in the last 60 years now. But there is another property to include, selection. Can the system select what it needs to build itself up? So if you have a vast diversity of bricks, of stones, can they automatically select what it needs? It can. This virus has done it too, so the example was already there. You need diversity, you need dynamics, you need the objects to be able to dissociate and reassociate, and this then leads to what we call the constitutional dynamic chemistry. That means the dynamic chemistry which resides in the constitution of the object. It's not something moving. It's not something changing conformation. It's something which breaks the object and reassembles it, and perhaps differently, because if the conditions change after breaking and before reassociating, then you have also an adaptation possible. The object will be different, will be adapting to the new conditions, and this is then adaptive chemistry, which is now what we mostly do. This adaptive chemistry can be applied for a search for biologically active substances, because if you have all this collection of bricks and you put in, for instance, an enzyme, the enzyme will be the lock which will select the key. In other words, it looks sort of ideal. The lock selects the keys to get in. It will self-assemble. Then you can also have dynamic nanostructures and dynamic materials and technologies. For instance, for materials, the fact that you can make polymers which disintegrate and reintegrate and in a different way. Now, I want just to insist on some features which you certainly know about chemistry, which is chemistry has a creative side. It's a creative science. These are pictures here. We call creation something for arts. But science is as creative as arts. And because chemistry can create novel expression of matter, more and more complex. So the book of chemistry has to be written, not only to be read. And the score of chemistry has to be composed, not only to be played. So chemistry has a creative power, and this creative power is also already, many people have suggested something like that, but we can cite Leonardo, who is another famous Italian, and you can read the Italian, so I don't have to read you the English translation, but it's very clear that he had a very profound feeling about what happens. Man begins using natural things, atoms, molecules, in harmony with his very nature, the laws of nature, the physical laws, the way you put together two carbon, oxygen, and so on. And then the end is very strong, a creare infiniti specie, to create an infinity of species, very, very strong. And that means also that, of course, not just natural. Of course, when we have to investigate the world which is around us. When I started my PhD, I was doing natural product chemistry. Okay, I extracted birch tree, the bark of birch tree, and you have terpenes in there, and then you study the terpenes. But you can also make things, and most of what I told you does not exist in nature. So it's man-made, I should say human-made, because man these days forgets about women, but that is just a turn of the century. It's the same, we all know that man is, but human is not bad. Human-made is what one should say. In fact, I changed it on a slide, which I used this morning, I think in Sapienza. So let's go to mathematics, just to conclude, almost. David Hilbert, very famous mathematician, he's buried in Göttingen. He wanted to have two sentences of his tombstone. Wir müssen wissen, we must know. That's the beginning. Wir werden wissen, we will know. The beginning is that's push it, you want to know. But then the conviction, I think the faith you have into we will know. Now, how far we will know? We have made enormous progress in very few years. After what is 2 centuries in regard of the thousands of years of evolution of life, and of course, not to speak about the non-life. And this is thanks to science. And so, not for you, but it's for you too. You are young enough in your spirit to participate, because science shapes the future of humanity. And now I want to broaden a little bit. This is our planet, and nothing in the universe. Nothing. It's nothing. You don't see it. You need an electronic microscope, and you have to look at it. And science has no borders. And science is valid everywhere. Now, this is difficult. Again, saying that the periodic table is limited and saying that everything in the periodic table is valid everywhere is something which hurts me, which bothers me, because it's like a dogma, but it's inescapable. That's the point. Science has no borders, also because what we find on Earth is valid everywhere. That's why you can find water on Jupiter, on Enceladus, one of the planets around Saturn, because they now think that there's water there, and everywhere. If you see a far-off signal, which has both those signals, vibrations, How do you know there's water on that place? Here is dear Primo Levi, and that's his other book, which is very famous too. Thank you very much. I would just like something to add something that with Peter Gooditz, as I said, we started these European journals, and I think it was a way of trying to bring together countries and into science, because after all, science is valid everywhere. And I cannot understand that nowadays we have to spend money on arms. How stupid is it?
Thank you very much, Professor Len. I'm sure I'm reporting the feeling of everyone in heartful thanking you for being the voice of chemistry as an exceptional science which has a lot to say about the progress of mankind in the direction of peace and ethical values. And it is why you're known everywhere by everyone, not only because remarkably you are a Nobel laureate, but also because you're an ambassador of those values in science and in full harmony with the spirit of the Primo Levi Award. Thank you very much.